All right, for the non-calculator part, we're going to start with this table here at the right. So it says find the equation in point slope form. You've got to know what that one is. That's y minus y1 equals m times x minus x1. So find that equation of the line that passes through f of x when x is -1 and 2. So we need a point and a slope. So let's calculate the slope first. Remember, when you're given a table, you're kind of just thinking like average rate of change. We're using when x is -1 and when x is 2. So the 2 points that we're looking at here are -1, 1 and 2, -5. If it helps you, you could write them out like that. And so when I'm finding my slope, I'm really saying, all right, f of 2 is -5 minus the other y value, 1 over 2 minus -1. That's -6 on top. This becomes 2 plus 1, which is 3. So the slope that we're looking at is -2. And then use either one of these 2 points. So we're just doing point slope form. So either you can say, if I use the first point, y minus 1 equals -2 times x plus 1. Or you could use the other point, y plus 5 equals -2 times x minus 2. So either one of those is correct. You don't have to answer both. You just pick your favorite point. For number 4, write an equation that is perpendicular. So we'll have to think about opposite reciprocal slope to the line you found in problem 3. And it's got to pass through this point. So again, to write an equation for a line, we need a point and we need a slope. And we're using a perpendicular slope. So the slope I had in the previous problem was -2. The opposite reciprocal of that is positive 1/2. All right, write this equation in both point slope form and slope intercept form. If you need more practice on this, go back to the quiz, the first quiz that we took. Point slope form is what you should start with. So there's only one choice for this. There's only one point. Y minus 1/4 equals slope 1/2 times x minus 3. So this is point slope form. That's it for that. To get slope intercept form, which is y equals mx plus b, you can't just see what b is in the problem. You have to solve for it. So all you're going to do is take your point slope form and start getting y by itself. So distribute the 1/2. So it would be y minus 1/4 equals 1/2 x. 1/2 times -3 is minus 3 over 2. And then to get the b value, you have to add 1/4 over to this side. Right? So we get y equals 1/2 x. And then how do I do -3 over 2 plus 1/4? Remember, you have to get a common denominator. So multiply 3 over 2 by 2 over 2. -6 over 4 plus 1 over 4 equals -5 over 4. So you have to solve the point slope equation for y in order to get the form y equals mx plus b. All right, this is from section 6. Is f of x 1 to 1? And explain. So remember, 1 to 1 means does f of x have an inverse? So is f of x 1 to 1 is another way to say, does f of x have an inverse? All right, so let's look at f of x. 1 to 1 means no repeated y values, right? Every output has exactly one input. So look back at this table. At -5, the graph hits -5 at both plus and minus 2. Like you can graph these points and say, all right, -2, -5, -1, 1, 0, 3, 1, 1. Oh, that's a problem. 2, -5. If I were to graph this, it would fail the horizontal line test all over the place. All right, so is f of x 1 to 1? Make sure you answer the question yes or no. So no. And I'm just going to say f of x has no inverse. You could say is not 1 to 1. Whatever. And then you need to explain. Remember, you're not allowed to say that it failed the horizontal line test. You would say the outputs, here's what I can see exactly. The outputs of, curve this down, of -5 and what was the other output? -5 and 1 have 2 inputs each. That's not the only way to say that. You could reference the points like, yeah, I've got the point plus or minus 2, -5, and plus or minus 1, 1. That would work too. So some inputs have multiple outputs. You could say that too. Okay, domain and range. This is everybody's kind of dreaded thing. Now, remember, if this did not go so well for you on the first quiz, not only should you be practicing in this section, but also going back to that quiz and that review, and even that domain and range packet if you really want to, and practice it, right? You have all the answer keys. Blank copies are on Schoology, so there's lots of chances to practice. This is about starting to learn and memorize some rules. So maybe you make a study guide for yourself. Okay, number 6, find domain and range. So this should be jumping out at you by now. It's the square root of a backwards difference of squares. We've talked about this a lot this year. Here's the graph. That's a little half circle graph. And because it's square root of 36, the radius of that circle, that half circle, would be 6. So I know that it reaches up to 6, it goes to -6 and +6 left and right. So there's no algebra to do here. It's just the domain is -6 to 6. And the range, what's the bottom point? The bottom point is 0. And the top point is 6. All right. For number 7, we have a cube root function. Remember, cube roots have no issues for the domain. You can plug in positives, negatives, and 0. No issue. That's just all real numbers. For the range, same thing. We've talked about graphing now. So remember, the cube root graph kind of does one of these. That's a very rough sketch. So it does continue to go up and continue to go down very slowly, but it does hit all real numbers for the range. Now in number 8, when I move the cube root to a denominator, it's not the cube root that causes the problem. It's just the fact that it's in a denominator. So when I see a cube root in a denominator, I'm really just setting the expression 3x minus 5 not equal to 0. So that means that x cannot equal add 5 divide by 3. It cannot equal 5/3. And if I want to answer in interval notation, that's anything from -infinity up to 5/3, but not including, so we use parentheses, and anything after 5/3 to infinity. For the range, this is a rational function. We have a fraction here. So remember, you're thinking about pluses versus minuses. So 1 is 1 over a cube root. 1 is always positive, no matter what. So we're going to be dividing a positive number by a cube root. Now, we just said the cube root can come out as all reals. It can come out positive or negative. So sometimes I'll get positives. Sometimes when I divide, I'll get negatives overall. So that can be both positive and negative and positive. How do we say that in interval notation? Here are the negatives, -infinity up to 0, and 0 to infinity. And why am I excluding 0? Because remember, there's no x on the top. So there's no way that this fraction will ever be exactly 0. A fraction is 0 if you can get 0 on top. All right, number 9 is a square root function. So because it's a square root, we can only square root or we can only even root positive values. So for the domain, we need to ensure that 4 minus 12x remains greater than or equal to 0. So solve this for x, subtract 4, divide by -12. So flip this to x is less than or equal to, and then 4 divided by 12 is -4 divided by -12 is positive 1/3. So the domain is -infinity to positive 1/3, and there is a square bracket on that because you can take the square root of 0. This is not in a denominator. And then for the range, it's a square root function that has not been shifted vertically at all. So I don't have the exact graph for this. It's gone through a shift and a reflection and stuff. But remember, a square root function, square roots in general are always positive and they can hit 0. So always positive, including 0, would look like this. And then I've made a slight adjustment to number 10. So now I put the square root in the denominator. So when I'm talking about domain, The only thing that changes is that now 4 minus 12x can only be greater than 0. It can't equal 0 because then we would have negative 1 divided by 0, which is undefined. So I should be going through the same steps to solve this. I'm going to flip the inequality symbol when I divide by a negative. 4 divided by 12 is 1/3. So now it's just x is less than 1/3. So the only thing that changes is that you don't include 1/3 with a square bracket. All right, and then the range. I'm back to having a fraction, so I'm thinking about, okay, I've got a negative 1 over a square root. So negative 1 is always negative, no matter what. A square root, remember, is always positive. We just said that, too, in the previous problem. Square roots are always positive no matter what, because there's no negative out in front. So I will only ever have a negative divided by a positive, so I can only get negatives out of the range. So instead of, in my answer up here for 8, instead of negatives and positives, I only answer with the negative section. So negative infinity to 0. And again, g of x cannot equal 0 because there is no x in the top for that to happen. All right, for h of x, for the domain, this is a quadratic, so there's no radical, there's no denominator. The domain is all real numbers. With quadratics, remember, there is either a high point or a low point where the vertex is. So for the range, you might want to sketch this thing. We've talked about transformations. So this is x squared plus 15. So it's been vertically shifted up 15 units, and the graph opens up. So there's a vertex there at 0, 15. That means that the range is starting at 15 and going up to infinity. For number 12, 12 and 13, I wanted to put this on the review. They're kind of special cases. I know we've looked at these like way back in that domain and range packet, but not really since. So let's take a look at these. It's a square root function. So normally I would say, okay, 15 plus x squared needs to stay greater than or equal to 0. And you're supposed to factor this, put it on a number line, or maybe you start solving and you get like x squared greater than or equal to negative 15. Well, that's always the case, right? X squared plus 15 is always positive because when you square a number, it remains positive. And then when you add 15 to it, it's going to still be positive. So x squared plus 15 is always positive. That means that this inequality is always true. And if that's the case, it just means I can plug in whatever I want. So the domain is all reals because I can't get anything to be negative if I'm typing into 15 plus x squared. The range is a little tricky on that. Normally we say, okay, square root functions, they hit 0, they go up to infinity. But this one doesn't ever hit 0, right? X squared plus 15. The lowest you can go is if you plug in 0, you get radical 15. And then if you plug in anything after that, like plug in 1, now you get radical 16. Plug in negative 2, now you get radical 19. So it only goes up from there to infinity. And again, we haven't seen that. We saw that in our domain and range packet, the first one. But this is the only time that a square root function doesn't just start at 0 and go up. And then let's look at the other version of that. So on the opposite side, I changed it to negative 15 minus x squared under the square root. So think about this. Whatever you plug in for x squared will stay negative, and then you subtract 15 from it. So this is always negative. And so can I square root in always negative? No, there's nothing I can plug in for x to make this work. So this domain is actually no solution. This function can't exist. And same thing with the range. If I can't get a domain, I can't get a range either. If you try to graph this, let's just try. Clear this stuff out. So if I try to do the square root of negative 15 minus x squared, and let's just zoom 6, nothing shows up. If I go to the table, it's just full of errors because none of these are defined values. Okay, and number 14, be on the lookout for these. I like to put them in to the review, and also we've had this scenario in quizzes and tests. What type of function is h of x? Just because I see a fraction doesn't mean I blindly start going through this. Remember, dividing by just a number means you could do 2 over 6 is 1/3, x. 3 over 6 is 1/2. So this is a little easier to see in this form. This is just a linear function. So what's the domain of a linear function? All reals. And what's the range? All reals. We also see this trick in difference quotient. Remember, if you can recognize that that's linear, it makes life a lot easier for difference quotient too. Speaking of which, what is the formula for difference quotient? So you need to have this memorized. The slope of a secant line is equal to f of x plus h. Some of you on your quiz had minus h right there. Minus f of x all over h. What does the difference quotient represent? I kind of have it in the equation. It is the slope between any 2 points on f of x. The h is just like how far apart are the 2 points. You don't have to put that in. All right, so find and simplify the difference quotient for each function. So here's my function. I'm going to start with m secant equals. All right, so f of x plus h means plug x plus h into both any input section, any term that has the input, I should say, here. So that's like x plus h to the third minus 2 times x plus h. And then minus f of x means minus all of f of x. So put that in parentheses. And then it's all over h. Do not skip the all over h part. It doesn't take long to write. You should be trying to write legibly enough that you can fit that in your work. I just want you to have precise math. Remember, there's a shortcut to cubing a binomial. If you don't remember it, then you've got to cube it out the long way, which is to multiply x plus h times itself, get that answer, and multiply it by a third one. But remember, the shortcut, Pascal's triangle, was 1, 3, 3, 1. And that meant that we get 1x to the third plus 3x squared h plus 3xh squared plus h to the third. And then we're going to distribute a negative 2 through, so minus 2x minus 2h. Distribute a negative through, minus x to the third plus 2x. All of this is still over h. If we've done our algebra correctly, then the non-h terms should be canceling themselves out, meaning they add up to 0. So x to the third minus x to the third is 0. Negative 2x plus 2x is 0. So I am left with all of the h terms. And then you don't have to write this separately. I'm just doing it to point out what's left. It's easy to lose track of this term right here, so it is a good idea to write it out one more time. You don't have to. Because I can divide every single term by h, I can just go through and do that. So I get 3x squared plus 3xh plus h squared minus 2. You could also, you could say the reason we're allowed to do that is because we can factor an h out of the top and then cancel that h with the one down here. That's the longest difference quotient we have. Next longest would be if g of x is quadratic. So this is going to be g of x plus h. All right, so m secant equals negative 2 times x plus h squared plus 3 times x plus h. So that's putting x plus h in, minus all of g of x minus this negative 2x squared plus 3x. The whole thing's over h. Negative 2 times, square this out, x squared plus 2xh. Some of you on your quiz, you had just xh, but it's 2xh plus h squared. Distribute the 3 through, plus 3x plus 3h. Distribute the negative through, plus 2x squared minus 3x. All of that's over h. Distribute the negative 2 through as well. Negative 2x squared minus 4xh minus 2h squared. Then I'm just copying all these terms down. All of this is still over h. Okay, now non-h terms cancel. Negative 2x squared plus 2x squared plus 3x minus 3x. If you don't want to rewrite the line with the h's, just circle what you have left, because like I said, it's this one right here, the last h term, that is easy to overlook. So my slope of my secant line, if I divide by h, is negative 4x minus 2h to the first plus 3. Okay, now I have a hint here. Stop and think about this one. We had this in the review for the first quiz. We had this on the quiz. Here it is on this review. There's a good chance this might show up on our test again, right? So stop and think about this one. What kind of function is this? We had a cubic. We had a quadratic. What else do we typically do this with? Linear. All right, so divide each term by 12, just like you're allowed to divide each term by h. 3 over 12 is 1/4. 6 over 12 is 1/2, so minus 1/2 x. This is linear. And what is the slope? It's the number that's being multiplied by x. So m secant, the slope between any 2 points on this line, is negative 1/2. I don't have to actually do the difference quotient to get that answer. And I want you to skip the difference quotient because I want you to understand that we are finding the slope between any 2 points on the function. And if it's linear, you don't have to use this whole formula. Okay, now we're on to our table stuff. So complete the table and use it to answer these questions. F of x is odd, which means the signs will be opposite on opposite x's. And g of x is even, which means the signs will be the same. So again, maybe you write a note to yourself. Oh, not odd, sorry. Maybe you write a note to yourself. Opposite, same. What does that mean? For if I'm writing opposite for f of x, at negative 4, f is 2. So at positive 4, f has to be negative 2. At negative 3, x is 3. At 3, x has to be negative 3. Now go the other way. At 2, x is negative 1. So at negative 2, it's got to be positive 1. At 1, I get negative 4. So at negative 1, I've got to get positive 4. So these have the opposite sign of these. Now, if I have the same thing, then I should just be copying over. For g, if negative 4 gives me an input of negative 4 gives me an output of 0, same thing happens at 4. I get 0. For 3, let's see. For 3, I get 1. So at negative 3, I also get 1. At negative 2, I get negative 2. Same thing has to happen at positive 2. I get negative 2. And at negative 1, I get 2, because at 1, I also get 2. All right, once you have this filled in, you're evaluating stuff. So f of negative 2 plus g of negative 3. So when I put in negative 2, remember these are inputs, and then these are outputs. So when I put in negative 2, I get out 1. And when I put in negative 3 to g, I get out 1. So 1 plus 1 is 2. It's not the computation that's hard. It's finding the correct value in the table. Okay, so here, start on the inside. This is f of g of 3. So what is g of 3? So when I put in 3, I get out 1 from g. And then now go to f. When you put in 1, you get out negative 4. G of f of negative 1. So start with f of negative 1. When you put in negative 1, you get out 4 for f. So now it's g of 4. When you put in 4, you get out 0. For this one, f of 2, when you put in 2, you get out negative 1. For g, when you put in 0, you get out 0. Anything divided by 0 is undefined. All right. Looking at behavior of a graph, list all relative extrema and identify as a relative max or relative min. And then what is the definition of a relative extrema? So how about we start there? What's the definition of a relative max or min? So relative, I'm abbreviating here, extrema are points where, let's just call it f of x, changes from increasing to decreasing, or vice versa. You can write out vice versa, or you could say that means or decreasing to increasing. Okay, so that's the definition done. And then what are they? Okay, so relative, let's just start relative max. Relative max is where you're changing over from increasing to decreasing, so like right here. So that just happens at point C. And then there are two relative minimum points. There's one down here at A, and there's one down here at E. So A and E. List points of inflection. What is the definition of a point of inflection? Again, that was a question on your quiz review and quiz, and here it is again. So start with the definition. A point of inflection is where f of x, I just say changes concavity. On your quiz, if you did not get this right, some of you were saying like it's the middle of the graph or something like that, but it's just where it changes concave up to concave down or the other way around. Okay, so where does that happen? There are actually two places. So the graph is concave up to begin with, and then it switches to concave down here, and then it switches back to concave up. So there are 2 points of inflection. They're at B and D. Okay, write the intervals where the function is increasing, decreasing, or constant. So not the rate of change, just the function itself. Okay, so let's start with increasing. The function is increasing, let's see, from A to C, right? And then it increases again from E to infinity. So A to C and E to infinity. Remember to always use parentheses. You won't use square brackets for anything except for domain and range. Where is the graph decreasing? It's decreasing on the far left and then here in the middle. So it's decreasing from negative infinity to A and then also between C to E. Okay, write the intervals where the function is concave up and concave down. So I drew this in. Let me get some of my marks out of here so it's less confusing. I drew in the concavity to begin with. So concave up is this first section all the way up until B. So that's one of them. So let's start there. Concave up was negative infinity all the way until you get to B. And then there's another concave up section from D to infinity. This last portion here is concave up. So D to infinity. And then concave down is this middle section here, and it stretches from B to D. So concave down, B to D. All right, for the table, so some of this, again, we kind of already filled in, but filling out this table, this is kind of a nice way to see how things are connected. So we've already answered a little bit of this. Now let's look at each interval. So let me make this smaller so I can fit it all in here. So again, I'm going to erase what I have here. We're looking from negative infinity to A. Is that function increasing or decreasing? So from negative infinity to A, it's decreasing. Let's go down the column here. Is the rate of change positive or negative? Well, if the function is decreasing, that means that the slopes between any 2 points on that function are going to be negative. The graph is going down. Is that part of the function concave up or concave down? It's on the concave up section. CCU is what I'm using to abbreviate that. And then are the rates of change then increasing or decreasing? Remember, a concave up portion of a graph has increasing rates of change. They start out really negative, and then as you get closer to A, they switch over to 0, and then they become positive. So those numbers are increasing. It's not about steepness. It's about the numbers for the slope. So notice how function decreasing correlates to negative rate of change. Function concave up means rate of change is increasing. Let's do it for A to B. So again, get all of this off. So A to B, is the function increasing or decreasing? Definitely going up. So increasing. And remember what that means. That means the slope between those points would be positive. So increasing goes with positive. And then is the function concave up or concave down? It's still on the concave up portion, which means that the rates of change are still increasing. They're going from 0 to something more positive. Okay, take a look at B to C. So B to C is this little section here. The graph is still going up on that section. So the function is increasing. And that means that the rate of change would still be a positive slope. So notice the pattern there. If you have increasing here, you have positive here. This is where the graph switched over to concave down in this little section here, right? From B to D. Yeah, right? That's what we answer for 27. So concave down. And what that means about the rates of change then is that the rates of change, the slopes are decreasing. They're going from zero, to negatives again. All right, let's get on to the next section. So D to E, that graph is still decreasing, that portion of the graph, which means the rate of change would be negative. Oh, I highlighted the wrong section. Sorry. C to D, right here. C to D. So decreasing, negative. That portion of the graph is concave down, and that means that the rates of change are decreasing. Okay, now we're on the next section, D to E. So this graph is still decreasing here, which means the rate of change is negative. This is on a concave up section, concave up, and that means that the rates of change are increasing. They're going from negative to less negative, closer to zero. And finally, our last section here. So now we're looking at E and beyond. The graph is definitely increasing on that section. That slope would be very positive. This portion of the graph is concave up, which means rates of change are increasing. Okay, so study the connection between concavity and rate of change increasing or decreasing, and function behavior and whether that's a positive or negative rate of change. On which interval is the rate of change both positive and increasing? Well, this table is really nice, but positive and increasing means positive means going up. Increasing rate of change means concave up. So we're looking for a combination of the two like that. Or check your chart. Positive and an increasing rate of change. That looks like A to B. And E to infinity. Let's look. So A to B has this little curvature, and E to infinity has the same thing. So A to B and E to infinity. Okay, on which interval is the rate of change negative, going down, and decreasing, which is concave down? Oh, sorry, negative and increasing. So going down, increasing is still concave up. So that would look like this, kind of. So you can use your chart, or you can go and say, all right, decreasing but concave up was this little section here, D to E. All right, I'm going to cut my video off here because it's almost time for the next class, but I will put my final video will be this, this last page with the graphing and stuff.